Cosmic inflation. You've probably heard of it. It's one of the most important, most powerful ideas in all of physics, trying to explain the very first moments of, well, everything. But it's also one of the most controversial. Some physicists think it might not even be science at all. So let's dive into this cosmic smackdown. So right off the bat, here's the big question that gets people all fired up on Reddit threads and in university physics departments. Is this theory a brilliant key to understanding the universe, or is it, as one person put it, just utter nonsense? To even begin to answer that, we gotta go back to the beginning and understand why we even needed this idea in the first place. All right, Section 1, Fixing the Big Bang. See, before we can get into the drama and the debate, we need to talk about the problems. The standard Big Bang model is amazing, but it wasn't quite perfect. It left a few, really big puzzles on the table that inflation was cooked up to solve. Yeah, I mean, the Big Bang theory itself, it's a huge success story, right? But it had these nagging questions about the very beginning. It's like the theory told us the story of the universe, but the first chapter just didn't quite add up. The starting conditions just seemed a little too perfect, you know? All right, so here are the two big head scratchers. First up, the horizon problem. Basically, why is the universe so smooth? You look in one direction, you look in the complete opposite direction, and the temperature is almost exactly the same. But according to the standard Big Bang, those two spots should never have been able to, well, talk to each other. They were too far apart. So how'd they agree on a temperature? Then there's the flatness problem. Our universe is incredibly, weirdly flat. Any little bit of curve at the beginning should have gotten way bigger over 13.8 billion years, but it didn't. And inflation? It comes in with this one beautiful, almost ridiculously simple idea. What if, for a tiny, tiny fraction of a second, the universe just whoosh, expanded at an insane speed? That would smooth everything out, like stretching a wrinkled sheet, and solve both problems in one fell swoop. I mean, that's a brilliant idea, right? Super elegant. But this is physics. You can't just have a cool story. You need proof. You need data. And that raises a huge question. How in the world do you find evidence for something that happened in, like, the first nothingth of a second of time? Well, it turns out an explosion that big would have left behind echoes, a faint fingerprint left on the oldest light in the entire universe. And so the hunt was on. And that oldest light is called the cosmic microwave background, the CMB. You can think of it as the universe's baby picture. It's literally the afterglow of the Big Bang, a snapshot from when the cosmos was just a toddler, about 380,000 years old. And the prediction was clear. If inflation really happened, it would have stretched tiny quantum jitters into specific patterns of hot and cold spots in that baby picture. So, to go looking for this pattern, the European Space Agency sent up the Planck satellite. This was its whole job from 2009 to 2013. Stare at that ancient light and map it with more precision than ever before. It was basically the championship game for the theory of inflation. A real make-or-break moment. And the results? They were absolutely stunning. The data that came back from Planck, it was an almost perfect textbook match for what inflation predicted. I mean, listen to the project scientist Jan Tower. He basically said, yep, the measurements prove it. It looked like a total slam dunk. Case closed, right? Well, not so fast. This is where the story gets really, really weird. Because when physicists dug deeper into the math behind inflation, they realized it didn't just predict our universe. It predicted something else. Something wild and something that would kickstart this whole massive debate. Right. Section 3, a self-reproducing universe. Yeah, you heard that right. The very thing that made our universe so nice and smooth might still be going on, just somewhere else. Creating universe after universe, forever. Okay, so just to recap, inflation is this super fast expansion that ironed out all the wrinkles in our early universe. But here's the thing, it's all based on quantum mechanics. And in the quantum world, everything is, well, kind of fuzzy and random. You have these little quantum fluctuations popping in and out of existence constantly. And this is the killer idea. The theory says that in our little corner of the cosmos, inflation stopped. It slowed down, and that allowed our universe to cool and form stars and galaxies and, well, us. But in other places, those random quantum fluctuations could have kept the inflation engine running. And that leads to this mind-bending concept called eternal inflation. The idea is that the whole cosmos is like a bubbling pot of water, and our universe is just one bubble that cooled off. But the pot itself is still boiling, constantly creating new bubble universes, maybe even with totally different laws of physics. And the craziest part? This wasn't something they tacked on for fun. It seems to pop right out of the original math. And this is where the fight starts. This idea of a multiverse that we can't see, can't touch, can't ever visit, it basically split the physics world right down the middle. Okay, so in one corner, you've got the people who are all in on inflation. Their argument, like this Reddit user puts it, is pretty simple. Hey, the theory works. It solves the Big Bang's problems. Its predictions about our own universe were proven right by Planck. So what if its biggest consequence, the multiverse, is really, really hard to test? That doesn't make it wrong. Science is supposed to be hard. But then, in the other corner, you have the critics, and they are not holding back. This user just calls it utter nonsense. For them, the argument is just as clear. If your theory's main prediction is something that is fundamentally untestable forever, then you've left the realm of science. You're not doing physics anymore, you're doing philosophy. And that really is the question at the heart of this whole thing, isn't it? What do you do? What do you do when your most successful theory, the one that explains everything we see, also predicts something we can never see? Does it just stop being science at that point? Now, this isn't just people yelling at each other in forums. This is a real, technical, mathematical problem that physicists are trying to crack right now. And it all comes down to something called the measure problem. And look, this isn't some wacky fringe topic. This is dead center in the world of theoretical physics. You're looking at the cover of an actual PhD thesis from MIT all about this problem. And get this, it was supervised by Alan Guth himself, the guy who came up with inflation in the first place. That tells you how serious this is. So what is this measure problem? Well, it's pretty wild. If you have an infinite multiverse where inflation is always happening, then anything that can happen will happen, an infinite number of times. Think about that. That means there are an infinite number of universes where you're listening to this right now, and an infinite number where you're a pirate. It completely breaks the idea of probability. And if you can't calculate probabilities, you can't make predictions. A theory that predicts everything really predicts nothing. I mean, how do you even begin to calculate the odds of your own existence in a situation like that? If your theory can't tell you why our universe is the way it is, instead of one of the infinite other possibilities, then what's the point? So what physicists are trying to do is find a mathematical rule, a measure, to tame these infinities, to make sense of them so they can make predictions again. But so far, nobody's found one that everyone agrees on. And that's pretty much where things are today. Cosmic inflation is stuck in this bizarre paradox. On one hand, it's a spectacularly successful theory that describes our observable universe perfectly. On the other hand, it leads to this idea of an infinite multiverse that might just break physics itself. So, what is it? Is it the theory of everything we've been looking for? Or is it a Pandora's box that we can't figure out how to close? The debate, as they say, continues.